Okay, hello and welcome back to another one of these A-level maths videos. So again, we're still on statistics, and we're on one of the last parts of the data section of statistics, which is going to be correlation and regression. So let's go through. Okay, so if we have two pieces of data, right, let's call them XY for now. We have something similar to that, right? What we normally do is we can draw a line of best fit. In theory, it should be a straight line. And what this will help us do... Hello Nathan, how are you? And what this essentially allows us to do is have a look at the data and tell us if it's a positive correlation, negative correlation, or if there's no correlation at all. So what correlation means is that, in this sense, as x goes up, does y increase, decrease, or stay the same? So today we're going to be doing the correlation and regression part of A-level statistics, A-level math statistics. So I'm doing this as slowly as possible because statistics can be quite confusing, but we have all of the exam questions from the past few years ready to go. I'm just going to go through some of the notes for this at the beginning. So essentially this is what correlation tells us. It tells us what happens as we increase x. Okay? Now, x is normally called our independent variable in science or even in maths beforehand. However, with statistics we instead call it the explanatory variable, and the y we sometimes call that the dependent variable, or at least we used to, but now in A-level statistics we're going to be calling it the response variable. Okay? So sometimes in a question it might just be 1 mark and it might literally just say what is the response variable, what's the explanatory variable. So it's good to just know that. So that's pretty much it. However, the whole thing about regression is that when we draw a line of best fit, it's an approximation. In the same way, if you remember back at GCSE, remember when you had to find the gradient of a curve at a point, we drew a tangent and it was a approximation? Because we haven't calculated it, right? Like, I could change this line of best fit slightly and it would still be correct, but there is obviously a mathematically correct way of doing it. So the line of regression is simply the same as the line of best fit, but we are going to calculate it numerically. We're actually going to have a way of calculating it. Okay? And again, it's going to take the form. Technically, the form is just y equals mx plus b. However, in A-level statistics, sometimes they change it round to b plus ax. As an example, if you look, that's just the exact same thing, right? Okay. The next thing we need to do is obviously be able to work out if something's positive correlation, negative correlation, or no correlation. And the best way for us to do that is there is a number called the PMCC. I'm not going to go through too many of the notes because I don't think it's necessary. We're going to go on to exam questions in literally 2 seconds. And that is the product moment correlation coefficient. So it's an extremely long name, and I don't think it's really necessary. Okay, but essentially it's just a number that goes from -1 all the way up to +1, where +1 is perfect positive correlation. So perfect positive correlation. And -1 is perfect negative correlation. And obviously right in the middle there's going to be no correlation. So the closer the number is to 0, the less correlation there is. The more negative it is, the more negative correlation there is, the more positive it is, the more positive correlation. And that's pretty much all the notes you need to do. They will give you the product moment correlation coefficient. However, I would like to warn you that if you do older past papers, you did have to calculate this in the old spec. But in this spec, you don't need to do it. Okay? But that's essentially all there is for that. So, if we go on to some exam questions. So the first one thing here. So a football coach measures the heights and weights of 12 players. They give this data here. Height and weight. And get that. And it says draw a scatter graph for this information. So drawing an accurate scatter graph on this is pretty tricky. So I just found a way of plotting it here. So this is the scatter graph you should get. Shouldn't be too tricky for you to do, I imagine. But again, let me know if you would like me to go through it. But they normally give you the axes in the exam, but I didn't put that on here just yet. Okay. Now for part B, it says, give an interpretation of the correlation between the height and weight of the footballers. So if I have a look at this, as height increases, so does the weight, right? It seems like a very positive correlation. Okay. So when they say give an interpretation, all you're going to say is, you know, what does it mean, the fact that these increase? Well, all you have to do is literally write out what it says. So I'm going to actually write this by text. So, as the heights of the players increases, as the height of the players increases, their weight also increases. You could also say something like, taller players tend to weigh more. And both those would give you the mark. Okay. Maybe that's fairly obvious to you at the moment. However, it says the equation of the regression line is W equals 1.37 H minus 173. Okay? So the equation for the weight is just equal to 1.37 times the height minus 173. Okay? And remember, this regression line is going to give us our line of best fit. So something that, well, that was terrible. Something that looks something similar to that. For part B, so as the height of the player increases, this bit here. Yeah, okay. So, all they're asking you to do is to have a look at the graph and give your interpretation of the correlation. So, what I would say first is it positive or negative correlation? This is what you should think in your head. Right? Positive correlation is when as the x variable increases, so this variable here, the y should also increase. So basically, if the graph is going up and to the right, it's positive correlation. Okay? So that's the first thing I would do. So I looked at this graph and I saw as the height increases, so does the weight, right? So then you have to interpret that, the positive correlation. Well, all it's saying is as the heights of the players increases, their weight also increases. Does that make a bit more sense? Yeah, okay, perfect, Nathan. Where did the Discord go? I haven't finished it yet. I could just post the link though. Maybe I'll put the link in the chat at the end of the lesson, and that should be fine. Okay, perfect. So for C, give an interpretation of the gradient of the regression line. Well, think of it as just the gradient in a normal sense, right? So we have this straight line going through here. All we need to do is say what the gradient represents. So the gradient, all it represents is, so first of all, the weight is so W is the weight, right? And H is the height. So with the gradient of 1.37, all we're saying is for every centimetre gained in height, the player gains 1.37 kilograms in weight. When you're going over modelling, what kind of modelling? Like in pure or in statistics? If you're talking about like binomial distribution and things like that, that should be next week or the week after. Okay. So that's all you have to do for the gradient, okay? All you have to do is look at the number in front, right? So I'm looking at the 1.37, modelling for differentiation. It's a bit later on. The ratio will be x centimetres. Yeah, pretty much. So every time the height increases by 1, we're gaining 1.37 kilograms in weight. Yeah. So what you have to do is look at the number in front of the x variable and use that to your advantage, right? So weight is 1.37 times height. Okay. So modelling for differentiation will come up a bit later on, not just yet. Although I have videos for CIE A-level maths differentiation that are coming out soon. So for part D, it says, use the equation of the regression line to estimate the weight of a player who's 170 centimetres tall. All you have to do is substitute in h is 170. That's all you have to do. So then weight is equal to 1.37 times 170 minus 173. Okay, so then you can use a calculator. Which is 59.9 kilograms. Okay. Hopefully that's okay so far. Lastly, for part E, it says comment on the reliability of your estimate in part D. So this is a question that they're always going to ask you in A-level statistics, is comment on the reliability. So all you have to do is, this isn't the answer, this is just going to be some notes. If the value is inside the data range, it's reliable. If the value is outside the data range, unreliable. That's all you have to say. Okay? So, we subbed in 170 centimetres. Is 170 centimetres in this data range? It is, right? 170 is right here. So, because it's inside this data, right, we have data from around 170. That makes too noisy. Okay, I'll try and sort that out. I was pressing the keys a bit hard. Okay, so when I say data range, look at the range of values we have. We go from 160 centimetres to 200 centimetres, which means 170 centimetres is perfectly fine. So, it is reliable because 170 centimetres is inside the range of data. Okay? Does that make sense so far? Nathan, are you okay with this so far? Not really. Which bit is a bit shaky? So I'm trying to teach through using the exam questions. So was the substitution okay for part D? Or was it part E that you're a bit confused on. Okay. So I'll just go over this last bit again. It asks us to comment on the reliability of the estimate in part D, which was when we used the regression line to estimate the weight of a player is 170 centimeters tall. Okay? So, here's your conditions. If the value that you substituted in is inside the data range, it's a reliable estimate. If it's outside, it's unreliable. So in this case, we subbed in 170 centimeters. Now, if I look at my range of data, I go from 160 centimeters to 200. So it is reliable. If they asked me for 210 centimeters, or even 150 centimeters, those are not reliable because they're not on the graph. Okay? So that's all you have to remember. If it's inside the range of values, then you're fine. If it's outside, then you're not fine. Okay? And again, you're only looking at the value that you're actually substituting in. Okay. So, for the next part, we have, so again, these are like the questions that specifically involve linear regression in this. But obviously I've had to take out parts that are like not related to it. So 2021 paper 3, I just realised that I don't actually have the graph. Give me 1 second. Okay. Okay. So there's a scatter graph. And he took a random sample of 16 students from a school, and for each student recorded the number of letters in their last name, the number of letters in their first name. His results are shown in the scatter diagram on the next page. Describe the correlation between X and Y. So if we look here, can we see any kind of correlation? Well, it's ever so slightly negative, right? Like if I were to draw a little line going through this, maybe move it down a little bit, that would be roughly where your line of best fit would be. As you can see, the line's going down, therefore it is negative correlation. Mark suggests that parents with long last names tend to give their children shorter first names. Use the scatter diagram to comment on Mark's suggestion, giving a reason. So, if we look here, X is the last name, so I'm going to write last name next to it just to make it a bit clearer. First name. So as the length of the last name increases, the length of the first name does decrease. So it's sensible as there is negative correlation between the variables. Okay, so all that means is that as the length of the last name increases, the length of the first name does seem to decrease. Again, we can't be sure. And what tends to happen in the next couple of parts is that you're going to actually work out hypothesis testing. So you'd actually test whether or not it is indeed true. But that's coming up a bit later, so we're not going to do it today. The next question, so Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures £W and the average weekly temperature T degrees for 8 weeks during the summer. The product moment correlation coefficient for this data is minus 0.915. If you remember, it goes from -1 to +1. And this thing here is very close to -1, so it's strong negative correlation. That's what that's telling me. Stating your hypotheses clearly and using a 5% level of significance. So this is hypothesis testing, so we're not going to do this. However, I'm just going to write that it is actually negative. Okay? Then it says suggest a possible reason for this correlation. So why would, as the temperature increases, why would the sales figures decrease? Well, it could be that as the temperature increases, people tend to spend more time at the beach rather than shopping. Right? It could be something like that. So they'd rather be outside than inside shopping. So that could be one reason for it, but it's basically any sensible reason. So as temperature drops, people are more likely to go to shopping instead of the beach. As the temperature increases, people would rather be outside. If the temperature is large, then maybe they don't want to go shopping. Or less clothes needed as the temperature increases. Any of those is completely fine. Any valid suggestion. Now, Tesla suggests that a linear regression model could be used to model these data. State given a reason whether or not the correlation coefficient is consistent with this. Well, essentially, this is going to be like a straight line graph. So if R is away from 0, so the magnitude of R is closer to 1, then you can indeed use regression models. In this case, R is close to -1, so it is consistent. And then what would be the explanatory variable? So which one is the independent variable? Well, that's going to be the temperature. Why? Because sales are likely to depend on the temperature. Right? It makes more sense that the sales are affected by the temperature than the temperature being affected by the sales. Right? When I buy more clothes, it doesn't make the world hotter. Whereas if the world's hotter, it might affect how many clothes I buy. And lastly, we have, again, given interpretation of the gradient of this regression equation. Well, for every 1 degree or every degree rise in temperature leads to a drop in weekly sales of £171. Again, if you look at the thing here, we have the variable of temperature. It's 171 times, it's negative 171. So it's decreasing by 171 for every increase of T of 1. Lastly, the sample paper. So a meteorologist believes that there is a relationship between daily mean wind speed and the daily temperature. A random sample of 9 consecutive days is taken from past records from a town in the UK in July, and the relevant data is given in the table below. So the meteorologist calculated the product moment correlation coefficient for the last 9 days and obtained 0.609. So explain why a linear regression model based on these data is unreliable on a day when the mean temperature is 24 degrees. Well, if we look at the temperatures here, none of them are anywhere near 24 degrees, which means it's outside of the data range. So all you'd have to do is write 24 degrees is outside the data range, hence extrapolation will be needed. Anytime you extrapolate, it's unreliable. Okay. Part B says state what is measured by the product moment correlation coefficient. It's just the relationship between two variables, right? So how strongly they are tied together. Part C again is a hypothesis test, so we're going to skip that because we're doing that next week. So next week's going to be just doing probability distribution in general for binomial. Then it's going to be hypothesis testing. Then we'll move on to mechanics. And that will be okay. But yeah, that's pretty much everything for correlation and linear regression from the past few years. It shouldn't be too bad. It's mainly interpreting data and looking at different data sets. But again, next week we're definitely going to be doing the... so actually, let me double check exactly what we're doing.